Good day and welcome to you. Today we're going to deal with vectors, and in this lesson we're going to explain the principles which we use to draw vector diagrams. And vector diagrams are drawn so that we can add vectors together, and there's a number of ways of achieving that, and today we're going to be looking only at the head to tail method of adding two vectors. But before we get to that, let's just spend some time talking about what a vector is and why vectors are so useful to us in physics. So you would have seen this word vector in your study of physics, and you'd also have seen the definition of vector. Now, a vector is a quantity that has two things, that has magnitude, and magnitude is just size, okay, and also has direction. So vectors have magnitude and they have direction. And examples of vectors, there are lots of them that we have in our study of physics. Examples of vectors are things like force, momentum, velocity, and you can probably name a few others. So just think about that a moment and think about whether there are any other vectors which you can think of which I haven't put on this list. There are a lot. So anything which you can think about in physics, which is a quantity which has got a size and also has a direction, will be a vector. And the opposite of vectors are scalars. And scalars are quantities which have just a size, a magnitude, but don't have direction. And examples of scalars are quantities like speed, and there are many other examples of scalars which you can look at. The big difference between scalars and vectors comes in the way that we treat them when we need to combine them or to add them together. Now, I want to take you back to when you first learned how to add. This was probably in early grade school or junior school, and you would have learned how to add by looking at everyday objects. So, for example, you might have been told that 1 apple plus 2 apples, that gives us 3 apples. And that's always the case. So 1 apple plus 2 apples will give you 3 apples. That's what we call scalar addition. It's the addition of simple things, things which don't have direction. And when we introduce addition in mathematics, when you're first of all learning mathematics, we do things like, say, if you have a basket and that basket has got 1 apple in it, then you put 2 more apples in there. How many apples are there in total? And there are 3, and you can imagine that because it makes sense. You can see 1 apple, you can see another 2 going into the basket, and then you've got 3. But for vectors, there's a process which we call vector addition, which is similar to scalar addition, but takes into account direction. And the way that we'll explain that is we'll look at an object which is the subject of 2 forces. So let's take Jack. Now Jack has a car, and his car's got a problem, so Jack needs to push his car. So there's Jack's car. And Jack is going to be over here. And Jack is going to be pushing his car. Okay. Now let's say Jack applies a force in the forward direction. Okay, he's pushing the car. And that force, which is the push, is equal to 800 newtons. Okay. So Jack applies a force which is 800 newtons, which is to the right. But we all know that when you're pushing a car, the car will offer some kind of resistance. The resistance is made up of frictional forces and other forces which act on the car. So those forces are going to act in the backward direction, and we can represent them by a blue arrow, which I'm just going to put up here. And then we're going to say that those forces are 500 newtons. We've got a situation here where there's one body, which is the car, and that body is subject to 2 forces, 800 newtons to the right and 500 newtons to the left. And force is a vector. When we add those forces together, we are adding 800 newtons to 500 newtons. But you can see intuitively that the result is not going to be a simple addition of 800 plus 500, which would give us 1,300. So if this was a scalar addition, then we simply say 800 plus 500 gives us 1,300. Okay, so that would be 1,300 newtons. Right. But that's not the case. That's incorrect. Because when we are dealing with vectors, because vectors have got a direction, and it's obvious to see that force has got a direction, what we have is a push of 800 newtons to the right and a resistive force of 500 newtons to the left. Intuitively, you can see that the result of these is that the 500 will take away from the 800, and the result that you'll get will be 300 newtons, and that will be to the right. So 300 newtons. That will be the result of these two vectors. And what we've just seen is a simple vector addition. It's straightforward to understand this example because both vectors, that is the force to the right and the resistive force to the left, act along a straight line. So you can see that the 500 is easily separated from the 800. Okay. But to treat it properly, to be thorough about it, we could draw a vector diagram. And that vector diagram would look like this. We would find a scale. And using a scale, we would represent 800 newtons. And using the same scale, we'd represent 500 newtons. And then we would draw a diagram which would then give us the resultant. And that's what we're going to do next. So now we're going to see how we can draw a vector diagram to solve the simple problem of 800 newtons to the right and 500 newtons to the left. A vector diagram represents each vector as a line with an arrowhead at one end of the line showing the direction. So we could represent this 800 Newton vector by a line like that, where the length of the line, that length there, represents 800 newtons. And then we could represent the 500 Newton vector by a similar line. And this would be directed to the left, because that's the direction of the 500 Newton vector. And this length would represent 500 newtons. In order for us to do that, we must come up with a scale. And a scale is very important when we are drawing vector diagrams. In choosing a scale, you want to choose a scale which uses as much of the available space that you have for drawing the diagram as possible. Now, you're going to have to use a ruler. And here I've got a ruler, and the ruler is part of a set square, which is handy because sometimes you need to figure out right angles when you're drawing vector diagrams. So it's a useful idea to have a ruler which is a set square. But even if you've got just a standard 30 centimeter ruler, you can then draw accurate vector diagrams and get answers. So let's start off by choosing a scale. Okay, so the first thing that we need to deal with is scale. 800 newtons is the size of the force, the size of the vector. Okay. I could choose a scale where this 800 newtons was represented by 16 centimeters, because I've got 16 centimeters available on my ruler here, and I've got 16 centimeters which can fit into the space I've got to draw the diagram. So I could choose a scale where I could say 100 newtons is 2 centimeters. So 100 newtons is 2 centimeters. Another way of putting that is saying 1 centimeter is 50 newtons. So my scale could be 1 centimeter to 50 newtons. which would mean that this 800 Newton force would be a total length of 16 centimeters. Now I want you to stop and think about that for a moment. Make sure that you're happy with it. That if 1 centimeter is 50 newtons, 800 newtons is 16 centimeters. When we look at the 500 Newton force, the 500 Newton force converted on our scale would be 10 centimeters. So I can then represent my 800 Newton force as 16 centimeters. Okay. So that's 16 centimeters. Right? And I can represent my 500 Newton force as 10 centimeters. And we know that this force acts that way, and the 800 Newton force acts that way. And the way that I add these together is I simply put the head of one at the tail of the other. So in this case, the blue force, which is the 800 Newton force, has got a tail here and a head here. So this is the head and this is the tail. And so I put the tail of this force together with the head of the other one, and then I see that the difference here is a length which I can measure. So I can simply put my ruler down and I measure that, and I see that that length is 6 centimeters. And that length of 6 centimeters is actually to the right. So I can put a double arrow on it that way. And that 6 centimeter length converted on my scale, 6 centimeters represents, now when I convert it on my scale, 1 centimeter is 50 newtons. So 6 centimeters is 6 times 50, which is 300 newtons. And I've drawn my simple vector diagram. And that vector diagram has given me an answer of 300 newtons as a resultant force which would act on this car which was being pushed. Okay. That is the simplest example of a vector diagram which is just in one dimension, so along a straight line. The simple example that we looked at earlier on, as we said, is the simplest kind of vector diagram that we can have. Very often, vectors don't act along a straight line, so they act not just in one dimension, but in 2 dimensions or 3 dimensions. So we're going to have a look at what happens when we've got vectors which act in 2 dimensions. And here, I'm going to use displacement as an example. Displacement is a vector because displacement has got a direction. Displacement is a straight line distance with a direction. So let's imagine we have a girl called Jane. And Jane is going on a walk. Simple walk. Jane starts off at the origin, and the origin could be home. Okay? And Jane walks a distance of 3 kilometers in the northerly direction. So this is north. She then walks a further 4 kilometers in the easterly direction. Her displacement at the end of those 2 separate parts of her travel is given by this line here. Okay, that's her displacement. So you can easily see that when Jane has got a displacement of 3 kilometers followed by a displacement of 4 kilometers in the manner shown, the resultant displacement is represented by that. And that's actually a vector diagram. You notice that we've got the first vector, which is a 3 kilometer displacement, laid out like that. The second vector, the 4 kilometer displacement, is laid out like this. But here we see the head of the first vector meets the tail of the second vector. Okay. And the resultant is that we have this vector. Now, if we drew a scale diagram for this, we would then be able to measure the length of that vector. So we'd be able to measure this length here, and that length would give us Jane's final displacement. All right. So let's try that. We've got 3 kilometers and 4 kilometers. So let's first of all start off by choosing a scale. And the scale which I'm going to choose is I'm going to say that 1 centimeter is equal to 0.5 kilometers. If that is the case, then this displacement over there, which is 3 kilometers, is going to be represented by 6 centimeters. So I can write next to the 3 kilometers, 6 centimeters. And this displacement of 4 kilometers is going to be represented by 8 centimeters. Then I can go ahead and I can draw my diagram. It's quite straightforward. The diagram is as follows. We start off with 6 centimeters in the northerly direction. Right? And then that is followed, and here's where having a set square is really handy because you can draw good right angles, and that's followed by 8 centimeters in the easterly direction. And my resultant, which I'm going to draw in purple, is here. Okay, so that's my resultant. And I can measure the length of my resultant, and that works out to 10 centimeters. So this is 10 centimeters. So once I've got that length, what I can then do is I can convert that length into a displacement using my scale. And my scale says 1 centimeter is 0.5 kilometers. So this 10 centimeters then works out to 10 times 0.5, which is 5 kilometers. And I can go further. And if I would like to know the direction of Jane's displacement, then I can measure that angle. And to measure that angle, I need to use my protractor. It's very important to have a good protractor. I put that protractor in. Okay. And then I can measure this angle, and the angle works out to, we'll take it as 52 degrees. So that angle is 52 degrees. So I can say that Jane's final displacement is 5 kilometers in a direction which is 52 degrees east of north. And that's how I can draw a simple vector diagram which is in 2 dimensions.